All right, so we're continuing our survey of different types of spectroscopies here. And this video is going to be on photoelectron spectroscopy. But before we dive into that, just wanted to remind you that early on in the course, we went over vibrational spectroscopy. Remember that vibrational spectroscopy uses near-infrared light to excite vibrational modes in molecules. There's two flavors of this, right? We learned about infrared spectroscopy, which was an absorptive technique, and Raman spectroscopy, which was an effect that rose from light scattering off of molecules, okay? But now on to the meat of the video, which is about photoelectron spectroscopy, abbreviated as PES. This is a very powerful technique for inorganic chemists. I alluded to it a little bit earlier on in the course when we were talking about hybrid orbitals and how hybrid orbitals don't actually exist, okay? This is the main experimental evidence we have disproving hybrid orbitals, and actually it is the way in which we get the energy levels of the molecular orbitals in any molecules. And so what you're doing is you're shining monochromatic light onto a sample, and then you can have ionization occur. And so, you know, whatever that light is, monochromatic just means one wavelength, right? So you have one energy of that light, so that has some energy associated with it. We can calculate that using general chemistry principles, right? E equals h nu. And so that we're calling energy of photon. And then that energy is going to go into the molecule. And part of it is going to go into the binding energy of the electron. Okay, that's being excited. Now this electron is going to be ejected out of the molecule, and that's going to have some kinetic energy. Okay, but you're also going to have vibrational modes that are going to be excited within the molecule. Okay, and there's two different types of photoelectron spectroscopy. We're going to be focusing on ultraviolet photoelectron spectroscopy, also abbreviated as UPS. Ultraviolet light has the right energy to excite valence electrons in most types of molecules, okay? Contrast that with X-ray photoelectron spectroscopy, where you use X-ray light, okay? Recall that X-rays have more energy, right? Shorter wavelengths, higher frequency than ultraviolet light. And so as a result, you're going to be ejecting deeper electrons, more stable electrons, because you're shining more energy on it, higher energy light. So XPS is used to probe core electrons. And there's a lot of uses for XPS, typically more in the materials chemistry side of things, whereas UPS is used more in the inorganic chemistry side of things. All right, so we have this equation I showed you before where E photon equals E binding plus E vibrational plus E ejected electron. E just stands for energy. E binding is about equal to E of orbital. This is like the ionization energy, right? But it's the energy that orbital has, right? That electron is. So we can say that E photon minus E ejected electron, I just moved ejected electron to the other side of the equation here, is equal to E binding plus E vibrational. That's all that's left. And that is what we call the apparent IP, the apparent ionization potential, okay? And so what you're going to plot now when you get these spectra is the apparent ionization potential versus the number of electrons that are ejected, okay? All right, so there's that formula just shown again for you. And so if E vibrational is 0, and there's also actually E rotational in here, okay? If E vibrational is 0, and E rotational, that means that your apparent ionization potential is just going to be equal to the binding energy, which you can figure out because you know what frequency of light you shined at it, you know E photon, and you can measure E ejected electron, the kinetic energy of them. And so we're using a detector. And so from this, you can get the apparent ionization potential. And so what you end up seeing in this is some sort of x-axis. Sometimes it's increasing ionization potential to the right. Sometimes it's increasing ionization potential to the left. There's no really standard convention here. So you have to look carefully at the data that you're given. And then this is the intensity of the photoelectron spectrum. And so at this 0, 0 point, that's where your E vibrational and your E rotational equals 0. Meaning when you shine an electron at your molecule, the electron exited the molecule, okay, but the molecule did not go to an excited vibrational or a rotational state. That is the ionization potential, okay, that is the ionization potential of the orbital. Now, you see all these other bands here. This is for excited vibrational and to a lesser extent rotational. Remember, rotationals are very finely spaced bands. So unless you're doing very specific type of spectroscopies, you usually can't see them because they're very close in energy. But so these are vibrational fine structure, okay? So this first band would be like your no excitation in your vibrational state. This would be exciting to the first vibrational state, okay, second vibrational state, etc. And you can see there's a distribution here. And the fine structure is dictated by the harmonic oscillator, which hopefully you've learned in PChem. The frequency, right, is 1 over 2 pi over k, the force constant, which is like the bond strength, divided by the reduced mass. So the spacing between these vibrational fine structures is nu, okay, approximately, right? So you can see if you have, greater mass, you're gonna have lower nu, so you're gonna have finer spacings. If you have a greater bond strength, for example, you're going to have a bigger spacing, right? Because nu would be bigger. All right, so that's kind of the introduction to PES. Now next videos we'll go into some details of how it works and how to interpret spectra.